All right, today we'll think about just one thing, the Doppler effect. The Doppler effect is something that can happen with any kind of wave, but it's usually a little bit easier to think about it in the specific case of sound waves. The basic idea of the Doppler effect is that if the source of the wave is moving, or if the observer of the wave is moving, the frequency that the observer actually receives is different from the frequency at the source. So I've got a little example here of how that works in the case of a source that's moving and then the observer is standing still. Imagine that the observer is over here at the end of the blackboard, and the source is moving towards the observer as time goes by. So right at the beginning, time 0, when you first turn on the stopwatch, this source has been emitting waves for a while, and there's one region of higher than usual air pressure. If we were drawing wave fronts, there'd be this point would be a point on a circle that has the source as its center, and then after we wait for a time equal to 1 period, and in that much time the source has moved a little bit, and in that same amount of time this pulse has moved at a higher speed, the wave speed. And of course, in 1 period, it turns out that in 1 period, any one pulse or any one wavefront will move exactly 1 wavelength. So this distance is 1 wavelength, that distance is 1 wavelength. So by the time we get to the second time, the pulse is here. And then 1 period later, the pulse is here. A period after that, the pulse is here. And then a period after that, the pulse is here. But what else happens here? This source had emitted another pulse, and so in the time of 1 period, that landed here. So here's where we first see that pulse at the second time, and then the third time we look, 1 period after that, the pulse again has moved 1 wavelength, and then 1 period after that, here it is. 1 period after that, it's there. And now go 1 period later than this, the source has again moved a little bit. It's emitted, and in that time it's emitted another pulse, which during 1 period has traveled 1 wavelength, and then in the next time interval equal to 1 period, it travels this far and then travels this far. Now notice that over here at the observer, right at this time, say time 5, this pulse hits the observer, and then shortly after that, this pulse, which was here at time 5, will very shortly after that hit the observer. But notice that this distance here is much less than a wavelength. So traveling at the same wave speed as any other piece of this wave, it's going to take a much shorter time for this pulse to arrive here. So in other words, the time interval between the arrival of this pulse and the arrival of this pulse is pretty short compared to the amount of time between each pulse being emitted by the source. In the time of one period, every pulse travels one wavelength. So that distance there, that distance there are each a wavelength. But then this distance is much less than a wavelength. But when the pulses here are spaced closer together, the time between arrival of each subsequent pulse is a much shorter time. The period between arrival of one pulse and the arrival of the next pulse is much shorter, or to put it another way, the frequency at which pulses arrive here is a much higher frequency. So from the standpoint of the observer here, the frequency of the wave is higher, right? The frequency at which pick any one part of the wave shape, the frequency with which that shape arrives, and then the next point in the wave, just like that, arrives, is much shorter, because it's only had to travel a short distance. And so higher frequency when the source is moving towards the observer. If you turn that around and imagine a stationary source, but the observer moving, you get the same result, because imagine how it looks from the observer's point of view. If here we are standing over here, watching both the source and observer, we see the source stationary and the observer the observer stationary and the source moving towards the observer. From the observer's point of view, it appears as if the source is moving towards the observer. From our point of view, we see the source moving and the observer stationary. From the observer's point of view, the observer feels stationary and feels like the source is moving towards the observer. So in other words, whether we're looking at it from a standpoint here, somewhere in the outside world, or whether we look at it from the standpoint of the observer, in both cases we see essentially the same thing. We see the source moving towards the observer. And in both cases, whether it's source moving and a stationary observer, or observer moving and a stationary source, in either case, those two things, source and observer, are getting closer together. The distance between them is decreasing. And from the observer's point of view, since it looks to the observer like the source is approaching the observer is going to hear the same result. The pulses will arrive more frequently. In other words, the frequency of the sound wave will seem higher. So there are four different rules in the text for four different situations: stationary observer, and then source moving towards the observer or away from the observer, and then stationary source, and observer moving either towards the source or away from the source. It's a slightly different equation in each case, but one similarity: whenever the distance between source and observer is decreasing, the frequency the observer hears is higher than the frequency of oscillations at the source. And whenever source and observer are moving farther apart, the frequency that the observer feels is lower than the frequency at the source. So I'll just take a simple example here. Let's imagine that you hear an ambulance siren. You're just standing on the sidewalk. You are a stationary observer, in other words, and you hear the siren sounding at a certain pitch, at a certain frequency. And we'll call F prime, instead of just plain old F. F prime is the frequency that you hear. And we'll think about that frequency that you hear as a function of time. And then we'll say that F0 is the actual frequency at which the source is oscillating. And let's see what you actually hear is, let's say, something like this. For a few seconds, you hear a lower frequency than the actual frequency, and then suddenly switches to a higher frequency than the actual frequency. Well, this is the case that we already dealt with. You're stationary, and if the source is moving towards you, what you will hear is a higher pitch, a higher frequency than the frequency at the source. And as you might expect, you get the opposite result if the source is moving away from you. There's a nice diagram that illustrates this in the section on Doppler effect, and you should look at that diagram, think about it carefully. So anyway, anytime you hear the lower frequency, or lower than the actual frequency at the source, that means the ambulance was moving away from you. Like that. Now, let's take a more complicated case. Let's still consider a stationary observer and a moving source, but now a more complicated case. Let's imagine the speed of the source is changing. Right? The Doppler effect here is working exactly the same way at all times. That's a sign that the speed of the source is not changing. In this case, we'll look at both a graph and the actual equations. For a stationary observer and a moving source, the frequency that the observer actually hears is equal to the frequency at the source divided by 1, either plus or minus, minus or plus, speed of the source divided by speed of the wave, speed of the sound wave in this case. So, as you can see, whenever the source is moving, the denominator is different from 1, So the frequency that's actually heard by the observer is different from f0, the frequency at the source. And the minus sign corresponds to the source moving towards the observer, and the plus sign corresponds to the source moving away. Because if you've got a minus sign here, then this denominator is less than 1. So this whole fraction here, since it has a denominator less than 1, is greater than f0. You hear the higher frequency because the source is moving towards you. And if the source is moving away from you, then the denominator is greater than 1, so the value of this whole fraction is less than f0. And so the sound that you hear is a frequency lower than the frequency at the source. So let's imagine that this is going on. There's the frequency you hear, again as a function of time. Here's f0, the actual frequency at the source, and let's say what you hear is a frequency that's always changing, like that. Well, here in the first half of the motion, the frequency is changing, but it's always smaller than the actual frequency at the source, and that means that that the source was moving away. In a Doppler effect, whenever source and observer are getting farther and farther apart, the frequency the observer hears is always less than the frequency at the source. But the frequency is less than the actual frequency at the source, but that frequency is increasing and approaching the value of frequency at the source. What's happening there? Well, in this case, since you're moving away, or since the source is moving away from the observer, our equation is actually f0 over 1 plus that ratio of source over wave speed. And speed of sound isn't going to change. f0 isn't going to change. It is whatever it is, just depends on what's going on at the source. The only thing in this equation that could change is the speed of the source. Right? The ambulance that's sounding the siren either speeds up or slows down. But in this case, it must be slowing down, because as this decreases, the denominator decreases, so this fraction increases. The frequency you hear increases. Or put it another way, this gets smaller, means the denominator gets closer to just plain 1, which means this fraction gets closer to just plain f0. And then, of course, at this moment, the ambulance must have come, just for a moment, must have come to a stop. 0 speed for the source. In that case, this thing here is 0, and then the frequency you hear is exactly the frequency of the source. And now here, frequency is higher than the source. That always happens when source and observer are getting closer together. So in this case, now the ambulance is moving towards you. And so the right way to write the equation for the frequency that you hear looks like this. Frequency you hear is frequency of the source divided by 1 minus velocity of the source over velocity of the sound wave. So, in this case, the ambulance is now speeding up. How do we know that? As the ambulance speeds up, this fraction gets bigger. So then you're subtracting more and more from 1. And when you subtract more and more from something, you're left with less and less. In other words, when this increases, the denominator decreases. And if the denominator of a fraction decreases, then the fraction itself increases. So this is bigger than f0, and it keeps on getting bigger and bigger and bigger as long as the source speed is increasing. So here we had slowing down, and here we had speeding up. Or to put it in a much simpler way, the amount of Doppler effect that you actually get depends on the speed of whatever it is that's moving, the source in this case, where there is no speed, where the source has no speed at all, there is no Doppler effect. What you hear is exactly the source frequency. As the source speeds up, the frequency you hear becomes more and more different from the frequency at the source. And this going along the line, and now as you slow down, remember, you slow down here, as you slow down, you get less and less of a Doppler effect. The difference between the frequency you hear and the actual frequency of the source is smaller and smaller. Less and less speed of the source, less and less of a Doppler effect. More and more speed for the source, more and more of a Doppler effect. You could say the magnitude of the Doppler effect depends on the magnitude of the source's velocity. All right, that's all for today.